Hi everyone. So today we're going to talk about pH because for those of you who thought you never had to worry about pH again after general chemistry, in this class you're going to find out that you were quite mistaken because it turns out that pH is very important in biology. Our bodies are naturally buffered at a pH of 7.4 because all the chemical reactions in our body require a very specific pH. And in fact, the enzymatic reaction that we're studying, the lactate dehydrogenase reaction that converts lactate to pyruvate, is very dependent on pH. So let's begin by defining the pH. The pH is simply the negative log, and that's the log base 10 of the proton concentration in solution. So if we're dealing with a strong acid or base, in this case HCl, we would never represent HCl the chemically as this because HCl breaks down into its ionic components, H plus and Cl minus. And we can draw this reaction with a forward arrow indicating this reaction goes to completion because HCl and other strong acids 100% dissociate. So at any given time, HCl is never going to be HCl, it's going to be H plus and Cl minus. Now, for weak acids, such as acetic acid, yes, the acid that leads to vinegar having such a pungent taste, these guys go to less than 100% dissociation. And in fact, I think with acetic acid, it's like around 4%. And so with acetic acid, here's the structure. That's our ionizable proton there. So it's still going to break down in its respective parts. So it's conjugate acid or conjugate base of the proton there. But instead of representing this reaction as a forward arrow, we're going to see equilibrium arrows. Because unlike HCl, where we're only going to see the ionic components, with acetic acid, we're going to see, mostly acetic acid form and then a little bit of the acetate and proton, so the conjugate base and proton. Now, the equilibrium between these species is governed by the Ka, and so the Ka is equal to if you remember from general chemistry, the ratio of the products to the reactants. So if this is, we can abbreviate this guy as HAC, that's AC minus, and obviously H plus, would be equal to the ratio of the acetate conjugate base and the proton to the amount of undissociated acetic acid in the solution. Now, the Ka, at least for most, or at least for common acids and many chemicals with a dissociative proton, this value has been experimentally determined, is considered a constant, so it's something that is inherent to a chemical structure. And for acetic acid, we know that this value happens to be 1.8 times 10 to the negative 5. Now, I debated going through and showing how we can determine the pH of the solution, knowing the concentration of the acid and the Ka, but I decided that was just a lot of work, and so to save time, I will have you know that the pH is integrally related to the Ka and the concentration of the relative species. And so weak acids are much are much more complicated than strong bases, and they can be mathematically more annoying to deal with. But the ability of or the lack of ability for weak acids and bases to 100% dissociate is what actually makes them really good buffers and why we can exploit them for our purposes. And so some of you may remember the Henderson-Hasselbalch equation from general chemistry. So if the Henderson-Hasselbalch is the pH is equal to the pKa plus, I'll scoot that guy over, plus the log of the conjugate base over the acid, or the base and the conjugate acid, vice versa. So the pKa, as we learned, is intrinsic to the buffering system that we choose, but the pH is tied to the ratio of the conjugate base to the acid. So if we change the ratio of these components, then we're going to change the pH. So we can manipulate the relative quantities of the acid and the conjugate base to see resulting changes, to get the changes we want in the pH. All right. And just as a quick note, the pKa is simply equal to the negative log of the Ka. So the pKa that will be defined whenever you're doing a buffer problem is coming from an experimentally determined pKa, and then you, or Ka, and then you just take the negative log of it, just as an FYI. Okay, so one of the things that you're going to have to be doing in this lab, and that's going to come back and you're going to have to redo throughout the semester, is you're going to have to understand how to create a buffer from chemicals in the lab and then use strong acid or strong base to adjust that buffer to the desired pH that you would like. So what we're going to do is we're going to say we want 100 milliliters of 100 millimolar acetate buffer, or acetate acetic acid buffer. And we want a pH of 4.0. And we know from our pulled off the internet that we have a pK of around 4.7. Okay, great. So how will we make this buffer if we assume we start with 100, or assume we have sodium acetate. So let's say we have 1 molar sodium acetate solution and 6 molar HCl, and those are the only two things we have in the lab to work with. So you have sodium acetate, so that's going to be our conjugate base, or A minus, and 6 molar HCl. So again, just to draw out our reaction here, we have our acetic acid, and it's going to partially dissociate to form the AC minus, the acetate ion, and the H plus. So in this case, we have only AC minus. What happens is if we add 6 molar H plus and then Cl minus, the H plus is going to react with the AC minus to form more acetic acid. And so by adding HCl to the solution, we will increase the population of the acetic acid, decrease the relative population of the acetate and the H plus, and therefore drop the pH. All right, but I'm getting a little bit ahead of myself here. So the first thing we have to do is we have to figure out how much acetate solution do we need to add. So we have a liquid form, we have apparently an unlimited amount of 1 molar solution, and then how much do we need to make 100 mils of 100 millimolar? And so that's when we pull out another good friend from general chemistry, and that's the dilution equation. So M1V1 equals M2V2. So in this case, so this is the initial for what we have, and this is the final or what we need. Okay, so what we have is 1 molar sodium acetate. We don't know how much volume we need, but we know in the end we want 0.1, that was like a 10, sorry guys, 0.1 molar, and we want 0.1 liters of it because 100 mils equals 0.1 liters. So we can solve for the volume added. So V1 equals 0.1 molar times 0.1 liter, 1 molar sodium acetate. And then we need 10 milliliters of 1 molar sodium acetate. All right, so we only need 10 mils of that solution. Then we need to figure out how many milliliters of 6 molar HCl do we add. And this is where things get a little more complicated. So we're going to set up our Henderson-Hasselbalch equation. So we'll write that again down here. pH is equal to pKa plus the log of A minus over, or AC minus over HAC. We want a pH of 4. We know the pKa is 4.7 plus, we don't know the ratio of AC minus to HAC. So the first step to figure out how much acetic acid we need or how much hydrochloric acid we need to convert the sodium acetate to the correct amount of acetic acid is we need to figure out the ratio of acetate to acetic acid to achieve a ratio that's going to give us a pH of 4. And so to do that, we solve for the ratio here. So you have negative 0.7 is equal to the log of AC minus over HA. So 4.0 minus 4.7. Then we raise each of these guys to each side to the power of 10 to get rid of the log. Then we have 0.2 is equal to AC minus over HA, or 0.2 HA is equal to AC minus. Now here is where things can get a little conceptually tricky. This is something you might have missed back in Gen Chem or something that you need to brush up on. That's the fact that our buffer that we want a 100 milliliters of 100 millimolar sodium acetate plus acetic acid buffer. And so that gives us 100 mils, so 0.1 liters times 0.1 moles per liter means that we have a total amount of 0.01 moles of acetate and acetic acid in our 100 mils of buffer. So when we're referring to the molarity of the solution, we're referring to the total amount of acetic acid and acetate in that buffer. Now initially, we're going to have 0.01 moles of sodium of that acetate, that conjugate base. However, when we add HCl, some of that is going to stay the acetate ion. However, a certain amount is going to be converted into acetic acid. So it's really important that when you're going and you're doing this calculation, you make the connection that the total amount of moles in the buffer, you have to figure out how many of those moles are converted to the other thing when you add either the strong acid or the strong base. Okay, so we'll cross that out, go back to pink. Okay, so 0.28 HA is equal to AC minus. So we know that our total number of moles of acetic acid / acetate is going to be equal to 0.01 moles. So that's going to be equal of moles acetate plus moles of HA. It's going to be 0.01 moles. Going to be moles of HA plus 0.2 moles HA. So 0.01 is equal to 1.2 times the moles of HA. So we're going to get an answer of 0.01 divided by 1.2, 0.0083 moles of HA, and then moles of A minus is going to be equal to 0.01 minus 0.0083, and we'll get 0.0017 mole AC minus. Okay, so we just did this. We used the ratio of acetic acid to acetate at our desired pH to figure out the amount of moles of acetic acid and the amount of moles of acetate that we need to achieve the pH of 4. So now the question is, okay, so again, just to review, we write this reaction here, H plus. So initially we had 0.01 moles of oops, not quite. Okay, so initially we had 0 moles of acetic acid, and we had 0.01 moles of the acetate ion. However, after we add HCl, then we go to 0.0017 moles of acetate, and then we have 0.0083 moles of acetic acid. And so that means, so minus x plus x. So if we solve for the change that happens is we see, so if you'll notice that when we start with acetic acid, 0.083 moles of that acetate are then converted into acetic acid. So therefore 0.083 moles of HCl is what we need to convert the acetate into the acetic acid. Okay, so then the question is, we know how many moles of HCl we need. So how much do we need? What's the volume in milliliters that we need to add? So we have 0.0083 moles of acetate. We multiply that. We convert. Oops, let me correct that there. HAC. And whoops, that's actually a 1-to-1 ratio there. We can make that conversion again because we make the assumption that HCl is a strong acid, so it's 100% H plus and Cl minus. Then we divide by the molarity of the HCl we're adding, multiply it by 1,000 to get the milliliters, and that gives us a volume of, let me quick work it out. All right, so that means we need to add 1.38 mils of 6 molar HCl. And so ultimately to make our buffer, we're going to need, what was it? Okay, we need 10 mils of 1 molar sodium acetate, 1.38 mils of 6 molar HCl. What we do is we take those two guys, we put them in a graduated cylinder, and then we fill 200 mils with water. So ideally, in the lab, you would take it to about 90. You'd measure the pH, and then once you've checked you have the correct pH, you would adjust the volume to 100 mils. But practically speaking, that's what we have. Okay, so over the course of this term, we're going to be working with a chemical reaction that's going to produce a proton, and therefore cause the pH of the reaction to drop. So let's apply this hypothetical situation to our equilibrium. So let's say that we have a chemical reaction that produces 0.0001 moles of H plus per minute. What is the pH after 5 minutes? And is this still a good buffer? So the first thing we can do is we can figure out how many moles of proton are produced in 5 minutes. So if we have a rate of 0.0001 moles of H plus produced per minute, we multiply by 5 minutes, and then voila, we get 0.0005 moles of H plus of H plus total. There is no minute component because it's not a rate anymore. Okay, so then what I like to do is I like to set up a little table to help us visually. So if we write our equilibrium reaction for the last time, I promise. So if we're at time equals 0, so this is before the reaction starts where we just have our buffer hanging out at pH 4, initially we're going to have 0.0083 moles of acetic acid and 0.0017 moles of sodium acetate. And then our change, so our change over a 5 minute period, our change is equal to 0.0005. Now we're producing protons. So we're going to be subtracting moles from the acetate side, because when we add protons, we're going to convert the acetate to acetic acid, and then we're going to be adding the moles to the acetic acid as we produce acetic acid from the proton and the acetate. And as a result, at time equals 5, if we measure the pH at the end of the reaction, we should see is 0.0088 moles of acetic acid, 0.0012 moles of AC minus, and also H plus by extension. So if we were to measure the pH, 4.7 plus the log of 0.0012 over 0.0088. You can trust me that we would get a pH of 3.83. So now the question, is this in the effective buffering range of an acetate buffer? And to do that, I'm going to have to show you a pH plot here. So this is of a theoretical titration where we have the equivalence of OH minus added to, I guess, our acetic acid buffer. And what happens is the plots kind of look like this. And so the center of our range, so the pKa, we're going to be completely flat. And then what you'll notice is out, okay, let's see, 1, and is that, and so our pKa for acetic acid is around 4.7. So you're going to notice that from pH that's, oh, and this is pH here on the slide, that from a pH of pKa -1, so this is 3.7, all the way to a pH +1, so this would be 5.7, this area is going to be completely flat. So from a pH, so when we change the pH from pKa -1 all the way up to pKa +1, or the relative change between those guys is going to be pretty flat. So however, once we get out of the pKa range, once we change that ratio to be beyond pKa plus or -1, that the change in the pH is going to increase or drop off pretty steeply. And this corresponds to when we have the A minus to HA ratio. Oops, that's not a negative. The HA ratio between 0.1 and 10. So when we're within this ratio, we're going to resist changes in pH. However, once you get on the outside of that range, the pH is going to rise and fall pretty quickly. So again, that's when our pH is pKa plus or minus 1. And as you can see here, we're at a pH of 3.83, which is well within the range of an effective buffer.